So we're starting set theory. We did perms and coms. Perms and coms test is on Monday, right? That doesn't change. It's on Monday. You come on Monday, there's your test, right? But we're moving on with set theory, but we're still going to review as we go along till Monday. So tomorrow we're going to go through the answers on that quiz, okay? We'll go through them, make sure we know what we're doing. All right. So, set theory. Make sure if you have a phone out, it is away because you're paying attention. We're starting off with definitions. So the definitions we have are the natural numbers. What are the natural numbers? Anyone know?
0 to 9.
Nope. Close. You're very close.
1 to 9.
1 onwards. Yeah. So the natural numbers are the natural ones you count like when you're a little kid. That's how I remember it. They're naturally ones that when you start counting when you're little, you start at what? 1. I don't know any baby geniuses that go 0, 1, 2, 3. You naturally start counting at 1. I should have made my kids be baby geniuses who did whole numbers. So natural numbers are the ones you naturally count. So 1, 2, 3, 4, etc. Forever and ever. Then you have the whole numbers. The whole numbers are the natural numbers plus the number with a whole. What's the number with a whole? 0. And then all the natural numbers. So the whole numbers just contain the number 0. Then we got to about grade 7 and our lives changed. Never to ever be the same. We learned about integers. What are integers? Negatives. You're getting close. It's the next one. Negatives and positives. We learned there's negatives and positives in the world, right? So you can go from negative infinity, negative 3, negative 2, negative 1, 0, 1, 2, 3, positive infinity. Rational numbers. The rational numbers are the numbers that are rational and not crazy. So if you have a number that can turn into a fraction, it's rational. So a number that can turn into a fraction. So an example of this could be any of the previous numbers, right? So examples of rationals could be negative 3, negative 2, negative 1, 0, 1, 2, 3. Those are examples. Those work because I can turn them into fractions because I can just put them over the number 1, right? So I could turn them into fractions, so they're rationals as well. They're specifically other things, but they are also rationals. But also decimals that stop. So another example could be like 1.25. 1.25 I can turn into a fraction. And your calculator can do it for you. I'm going to show you how. So write 1.25 into your calculator. If some people's calculators are set to it, it does. So you hit enter, say that's your decimal, right? You want to turn that into a fraction, you could just go 1.25 math, enter, enter. 5/4. So it turns into a decimal, right? So it's rational. Also, repeating decimals turn into fractions, so they're rationals. If you want to turn a repeating decimal, though, you have to type in enough decimals so it bumps to the next line. So if I go 1.666 and I stop here, then it thinks it stops there, right? If I want it to be a repeating decimal, I have to actually show that it's like going on. And then I go math, enter, enter. 5/3. Right? And it rounds, I have a truncating and rounding, but it's actually 1.66666. If I go 1.66 and I go math, enter, enter, that's not 5/3, is it? It's a terminating decimal, 1.66. If I want it to be the repeating decimal, I have to keep going till it runs off the screen or bumps to the next line for some. So some people tell me this is a fraction. 1.12, 13, 14, 15, 16, 17, 18, 19, 110, 20, 21, 22, 23. Is that repeating or is that a pattern? That's a pattern. I still haven't repeated yet, right? 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. There's no repetition in there at all. I'm just doing a pattern, right? That is not a repeating decimal. That's an irrational number. So, let's go back. So, 1.6 with a dot over top, that's 1.6 repeating, that's rational. 1.1.234 with a bar over top means it's 234, 234, 234. That's repetition. That's irrational. But an example of irrational would be like 1.11, 12, 13, 14, 15. It seems like it's repeating, but it's not actually repeated yet at all. It's just patterning, right? Or like 1.678943288. Is it ever repeating? Is it stopping? No. In order to form a fraction, it has to repeat or stop or terminate. Okay? So repeating decimals or terminating decimals are rational. And non-repeating, non-terminating are irrational. And our favorite one is pi. Pi doesn't terminate and it doesn't repeat. It's just random. And then the reals? The reals is easy. All of those are the reals. Reals are rational, irrational, integers, whole numbers, naturals. So every single one of these is actually part of the real. Now, I know prime numbers get discussed in grade 6 for the first time, I believe. Prime numbers are what? Do you know? Remember? Remember the definition of a prime? Prime numbers are numbers that have only two factors. Factors are numbers that multiply by each other to get that number. So for example, 12 has factors of 1 and 12, 2 and 3, or 2 and 3, nope, 2 and 6, 3 and 4. All of those multiplied get me 12, right? So those are factors, okay? We start discussing in grade 6, the factors that make up something. So prime numbers have only two factors. And the key thing about this is they have to be the number 1 and the prime number. So for an example of that would be 3, let's say. The number 3 is prime. The only thing that multiplies to give me 3 is 1 times 3. So it's 1 and the prime number are the only things, the only factors that give me that number, right? Now 1, people will tell me is prime. They'll tell me the number 1 is prime. But the number 1 only has one factor. Itself. That's it. Because 1 times 1 is 1, right? You can't count that as two different numbers, is it? No. So 1 is neither prime nor composite. So we're going to write this. Above here is with a star. The number 1 is not prime. So when you go to list prime numbers, please do not list the number 1 as one of them. It is not. So prime numbers have only two factors, the number 1 and the prime number. So let's give some examples. What's the very first prime number? 2. 2 is actually the very first prime number and the only even. Because once I hit 4, I have 1 and 4, 2 and 2, right? So 2 is actually the first prime number and the only even number. So we have 2, then we have the number 3. What about 4? No, what about 5? What factors give me 5? 5 and 1, that's it. So 5 is, what about 6? 1 and 6 and 2 and 3. So 6 isn't prime. What about 7? Yeah, 1 and 7. What about 8? 1 and 8, 2 and 4. So no. 9? 1 and 9, 3 and 3. 10? 10 is 2 and 5. 1 and 10. 11? 13? 14, 15, 16, 17, 19, etc. Composite numbers have more than 2 factors. You list the examples of that. So an example of a composite, what's the first composite? 4. Is 1 prime or composite? It's neither. It's neither prime nor composite. So 4 is our first one, then 6, then 8. 9 is our first odd. 10, 12, 18, 20, etc. Multiples of 3. Anyone remember? Multiples of 3. 3, 6, 9, 12. Anything that's divisible by 3 is a multiple of 3. So an example would be 3, 6, 9, 12, 15, etc. So multiples of 6 would be 6, 12, 18, 24, things that you can have divisible by 6. Factors of 12. The factors of 12 are 1, 12, 2, 6, 3, and 4. So what are factors? Yeah, what you can divide into it that makes it even, or what multiplies to give you that number, right? And divisible by 5? 5, 10, 15, 20, kind of like multiples. It has to, you have to be able to divide 5 into it and not get a remainder, right?
So if you need to put multiples of 5, I can't put.
Well, technically they work back and forth, yeah. No. Divide by number. And have no remainder. Then we're going to flip over. Okay. In math, just be happy you don't have to handwrite it. I don't believe it. In mathematics, a set can be defined as a collection of distinct objects. So, for example, the number on the faces of the die form a set. Sets are usually denoted by capital letters or by a description inside curly brackets. An object in a set is referred to as an element. The number 5 is an element in the set's of the numbers of dice. So an example here, it says there are general ways of defining the contents of a set. So we're going to look at six-sided dice. Okay, we're looking at six-sided dice. And we're going to define the elements in it. So we would go, let A represent the elements in a six-sided dice. Okay? And then we use squiggly brackets. These squiggly brackets are important. The squiggly brackets actually mean the set of. If you don't use the squiggly brackets, you're not showing the set of, which is a problem. Okay? So, we do squiggly brackets and we go 1, 2, 3, 4, 5, 6, because those are the 6 options on our dice, correct? And so each of these is an element in the set of A. So if I said, is 6 an element in the set of A? You would say, yes. Is 2 an element in the set of A? Yes. Is 3 an element in the set of A? Yes. Is 7 an element in the set of A? Is 7 an element in the set of A?
Oh, no, it's.
No, it's not an option. Other ways you could describe it in words. So you could say the natural numbers less than 7. Natural numbers start at what? 1. And then less than 7, we go to the number 6. All right. Natural numbers start at 1, and less than 7, we go to 6, and we don't count the decimals in between, so it will cover 1 to 6. Then here it says use set builder notation. X is less than 7. X is an element of the natural numbers. All right. So we're going to recall the curly brackets together is read as the set of. Whenever you see the curly brackets, it means the set of. The line represents and is read as such that. So here I said X such that. Okay? The E represents and is read as a member of or an element of. Instead of member, we can say element. So X is an element of the natural numbers. This is something to note. The number of elements in the set A can be written as this. Little n of A. So the number of elements in set A can be written as n of A. In the above example, n of A would equal 6. Why? Because there's 6 elements. 1, 2, 3, 4, 5, and 6. Not because 6 is an element in there. N of A represents the number of elements that there are. Why would we ever ask for the number of elements? Well, in some cases, the number of elements could be 6 or 7 or 8, correct? If I asked you to put it in a numeric response and my answer was 1, 2, 3, 4, 5, 6, is that going to fit in a 4-box numeric response? No. But if I say determine the number of elements in A, you can answer 6, and that does fit in a numeric response, right? So sometimes you ask for the number of elements in so that it actually fits in a numeric response rather than listing what the elements are. Okay? Note, the number 2 belongs to set A, but the number 8 does not belong to set A. So to express this, we say 2 is an element of A. 8 is not an element of A. The order of listing the elements in the set doesn't matter. So you could say in the set of this is 1, 2, 3, 4, 5, 6. Or you could say it's 6, 5, 4, 3, 2, 1. Or you could say it's 1, 3, 2, 4, 5, 6, whatever you want. It can be listed out of order. The reason why I always list it in order is so you don't miss it. If you start listing them out of order, there's a chance you might miss an element that's actually in that set. So I always list them in order. So if this one was listed as 1, 2 or 2, 1, both of them would be correct and you'd have to keep them, mark them as correct. So we're going to look here. Consider the following 2 sets. Whole numbers less than or equal to 3. Whole numbers less than or equal to 3. So how we're going to write that is equals the set of what's in this set, less than or equal to 3. And it's whole numbers. What do I start at? 0. Because whole numbers, you start with the number with the whole, which is 0. And then my next one would be 1, 2. Do I include 3?
Yes.
Yes, because it says
Less than 4.
less than or equal to. If it just said less than, I would not include the 3. This is true. Q is even whole numbers less than 10. So what do I start at? 0, 2, 4, 6, 8. This time do I include 10? No, because it just says less than. So do I include the 10? No. I really wanted to remind myself. So in A, we listed the elements in each set. We did that already. B, complete the following. What does N of P mean? The number of elements in P, right? So how many elements are there in P? 4. N of Q, how many are in Q? 5. We're going to go through more terminology. This lesson is very heavy on definitions and terminology, and then we just use them throughout the rest of the unit. Okay, so the very first day is heavy on terminology. So, Betty is defining sets using non-negative single-digit numbers. Non-negative single digit. What's a single digit number? 0 to 9. And -1 to -9 is also single digits, right? But it says non-negatives. So we know, this is what we're going to put. A U equals, and I'll explain why. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are the numbers we're looking at, right? And we do this U with a horseshoe. Why do we do this U with a horseshoe? Because it's part of the universal set. Universal set is U with a horseshoe. Shape. Looking dealio. Make sure you're copying down. So, within the context of any problem in set theory, there generally is some largest set that we have in mind. So this large set that we're only allowed to choose numbers from. Okay? We refer to this as the universal set. It is the set that contains all the elements under consideration and relevant to the problem.
Does it use the lines on the top of it?
Yep. And it does because the U without the lines means union or. Totally different. So state the universal set for that above. Label the set U. If you already listed it up there, you've done it. Okay? So it's some big set that we're only allowed to choose numbers from. So we're only allowed to choose 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Because we need single-digit non-negative numbers. Okay? Then we head to our different sets. So E equals the even numbers. Now can we list all the even numbers in the world? Or do they have to be contained within the universal set? Contained within the universal set. Why are you happy about that? So you don't have to list bajillions of numbers, right? Bajillions real. So, how many of the universal set are even? 0, 2, 4, 6, 8. Close the squiggly bracket. We need the squiggly bracket because that means the setup. Yep.
So the universal set's not, is it always 0 to 9?
Nope. It'll change per question.
Oh, okay.
Yep. In this case, they just said the list of non-negative single-digit numbers. So that was our universal set. But it could be natural numbers. It could be the natural numbers less than 17.
So it's like a word bank like numbers.
Yeah, exactly. Whole numbers less than 7. So we're going to do 0, 1, 2, 3, 4, 5, 6. Do I include 7? Nope, because it doesn't say equal to. Odd numbers less than 7. 1, 3, 5, 7? Nope, because it says less than 7. Okay, we're going to use this to actually learn the terminology. So we're going to flip over. We're always going to revert back to these ones though, okay? A subset. A subset of a set is a set that contains some or all or possibly none of the elements from a previously defined set. All sets we deal with in the problem must be subsets of the universal set, and every set is a subset of itself. What the heck does that mean? So in set notation, the symbol, the side U, it looks like this. It's a side U, or a longer C, is used to represent the relationship between sets. For example, E is a subset of U, since all the elements in set E are in U. So set E, what was in E again? I'm going to list them up here. 0, 2, 4, 6, 8. What was in, was it L or O? O? L? L? What's the second one, L? It was what?
It was L.
L. And it was 0, less than 7. And then O was odd numbers less than 7, right? Okay. And then our universal set was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I normally write these on the board beside, but if people are missing, they're not going to be able to see my words when it's right up here. Okay, so we're saying that E is a subset of U. The only way we can say that that's true is if everything in E is in U. So E has 0, 2, 4, 6, 8. Does U have 0, 2, 4, 6, and 8? Yes. Does it have more? Yeah. Do I care? No. In order for this to be true, everything here needs to be in this one. This one can have more. I don't really care, but it has to have at least E. Okay? So E is a subset of the universal set. Is L a subset of the universal set? Is everything in L in the universal set? Mm-hmm. Came from there. What about O? Is O a subset of the universal set? Yep. This one gets people. It says in here, all sets we deal with in a problem must be subsets of the universal set, and every set is a subset of itself. So we can also say E is actually a subset of E. Why can we say that? Because everything in E is in E, right? So a set is a subset of itself. Then we have, is set E a subset of L? Is E, everything in E in L? 0, 2, 4, 6, not the 8, right? Is everything in E and L? No. Is most of E in L? Yes, but it doesn't matter. It doesn't matter if most of it's in, or only one thing is in, or none of it's in. It's not a subset unless all of it is in. So E is a subset of L. 0, 2, 4, 6, crap, 8 isn't in there. I just said crap really loudly on the podcast. Meh. Okay. Whatever. So 0, 2, 4, and 6 are in it, but not 8. Correct? So can we say that E is a subset of L? No. We would say E is not a subset of L. Is O a subset of L? Is everything in O in L? 1 from O is in L. 3 from O is in L. 5 from O is in L. So is everything in O in L? Yep. So this is true. O is a subset of L.